from here you probably need some reference, something that will kind of help you organize how you're going to deal with the vector portion of your piece of charge, and maybe even go a little further and figure out how are you going to break up your ring into small pieces. I looked at a lot of papers. You guys took not 20 minutes. You took several minutes to draw the picture, but you don't know where to start next. So your notes, useless to you if you can't figure out where to start next. If you're going to use something that has a DQ in it, then you probably need something over there in your picture that will represent a portion of the charge. Do that right now. How are you going to represent a piece of the charge? You need to start someplace. Staring at it's not going to make it happen. It's not going to suddenly appear in your head. That doesn't work. DQ means a piece of something. In this case, charge. So, if it were me, I'd just pick a spot. And I would pick a spot that would help me with my measurements. I'm going to pick a spot on the very top of the ring. I could pick any place. But I think angles are going to be a part of my answer. So if I can somehow draw this in such a way as to exaggerate the angles, that would be best for you. You guys are smart individuals, but you have to be thoughtful now. 3 weeks away from the exam. Well, at least the week of exams. Now, how do I deal with this relationship? Well, each piece of this relationship is something else I have to think about. This portion is a constant. I'm not going to do very much with that. This is how much the piece of charge is, the value of charge at that location. I will have to write something beyond DQ eventually. Something that I can add up, something I can sum. This part is how far away it is from the point of reference. So now might be a good time to indicate how far away is that point from my piece of reference or my point of reference. You need some geometry here, some things that will help if it's not clear. I mean, I'm going to just put R here, but I know that R can't be in my answer. Right? It's going to be based on something that was in the picture. So capital R could probably be in my answer. Z could probably be in my answer. But I don't think little r can be in my answer. And then the first thing I'm going to notice after doing this is that, well, this piece of the electric field, is like in that direction. Do I think every piece of this electric field is going to be in that direction? No, I don't. But I drew this out in such a way as to try and help me maybe identify how I can use the geometry to my advantage. Now, there are other things we will have to do, but at least I have a way of starting to set up my geometry here. The first thing I'm going to realize is, well, if I can't use R, I probably need to write R in terms of something else. I have choices here, and they're not hard. I saw that on a few pieces of paper. Good. Way to go. Pythagorean theorem. Senior in high school, got your Pythagorean theorem down. Very impressed with you all. Pat yourselves on the back. Good job. Probably going to have to also recognize that the actual part of the electric field I want is only the part that is in this direction. That for every piece that I have in this direction, I think I have another piece that's going to cancel it out. I'm looking at the geometry. There's no hard or fast rules here. You will have to use your imagination a bit. But there's only so many shapes. I think you can kind of identify that once you're within one of the shapes, it probably is going to work out. This is a circle. So I think I'm going to keep every contribution that's in this direction, and I'm not even going to consider the contributions that are in that direction. Excuse me. That means dealing with the geometry again, and I'm going to say that I'm probably going to have to take each actual component of the electric field and multiply by the cosine of whatever this angle is. I see a right triangle there. I'm just utilizing the information about the right triangle to make sure I scale that portion of the electric field. In October, when we were doing this for the first time, I would have been saying something to you about make sure you're taking a look at the direction of your contribution. And if you can cross out off-axis components, do so. Here we're doing it. We are not looking at the off-axis components, just looking along the axis that's in the x direction. We're going to add up all those pieces. Now, this helps. This begins to build what I feel is an appropriate, integral, something that I can maybe sum up. Still have my constant out front. That's not going to change anything. Don't have to worry about that. I've got dq. I'm going to probably have to find a different way to deal with that. R squared, got that. It's going to be just r squared plus z squared. And then I have cosine of theta. Now, I am pretty sure for every piece of charge, cosine theta is going to be the same. I mean, do you think the angle is going to change at all here? It doesn't look like it to me. In fact, I'd go one step further. I'm thinking this is a constant and this is a constant. I don't think any of those things change. No matter which portion of the ring I choose, they're all going to be the same distance away, and they're all going to be aiming that piece of electric field at the same angle. Now, if this were a disk of charge, that would not be true. But it's a ring of charge. So I'm pretty sure I could collect all of my constants together. Let's do that over here. All of my constants. Everything in the bracket is a constant. It won't change no matter which piece of charge I happen to use. So they're not even going to be part of this integration. In fact, just looking at that suggests I can integrate both sides and just sum from 0 to q and be okay. Now, yes, last semester I would have forced you to say dq is probably some kind of linear density times ds. And then I would have said you need to break up the linear density into something like maybe the linear density is q over 2 pi r ds. And then I would have probably made you integrate around the circle. I might have even gone further and had you do q over 2 pi r and ds is r d theta and integrate from 0 to 2 pi. All to just prove to you that you can add it up by breaking up into little pieces. Doing this route right here has more flexibility in it. It allows you to deal with different situations that aren't so perfectly symmetrical. That was October. We're in the clutch now. We're in the point where half of you just took the time to draw the picture, making it look like you were working when you really knew where to start. That's a lot of you. You're going to have to get past that. Or not, and just not get the points for this question. Now, at this point, we can't actually have this be our answer. You would have to do more. And even if you recognize that the electric field is 1 over 4 pi epsilon naught times 1 over r squared plus z squared times cosine theta times q, that still can't be our answer. Theta was never a part of the problem. We can't leave it in terms of theta. We'll have to put theta in terms of other things that we are allowed to use. That means going back over here and figuring out some other way to deal with cosine. That's where you notice that this angle is the same as theta. And if I want to use the cosine of that angle, then I probably could use the triangle that's there. Z over r squared plus z squared to the 1/2 power. That's the cosine. All of this stuff we've done a couple hundred times. Well, maybe not 100 times, but all this we've done a bunch. This is review, so I'm expecting that the next time I put this on, say, a test, and you have reviewed it. Now, that gives us the answer that I'd like you to have. And it has all of the features we talked about on Friday, meaning E goes to 0 as Z goes to 0. You should know what that statement says. Some of you don't, but when Z is 0, where are we? Right, we're in the middle of the ring. So there's no electric field there because we have an equal amount of charge all around us. So all electric field contributions point in opposition to each other. They all cancel out. And E goes to a point charge as Z becomes much bigger than R. Right? The ring begins to look more and more like a dot the further away I get from it. And you can see that here. Right? When Z is much bigger than R, that term goes away. Z squared to the 3/2 is Z cubed. Z over Z cubed is 1 over Z squared. I'm expecting you to see these things now. Now, you guys are smart cookies out there. You now know things. Like you should be able to figure out how to find out what the maximum of this function is. You have a method to do so. Bless you. If you don't remember the method, probably something about taking the derivative, setting a derivative equal to 0, or plugging it into your calculator and letting the calculator do it. But you have a method for figuring out how to maximize or find maximums or minimums of an equation. So you should have that as something that's in your repertoire. Also, now that you have an expression for the electric field, you should be able to tell me the electric potential in, say, going from a point at infinity to 0. Because I think a very common mistake will be to look at this problem and assume that because the electric field is 0 at the center of the ring, that the electric potential is 0 at the center of the ring. And it is not. Would it take work to get to the center of the ring?
Yes.
If it takes work to get to the center of the ring, then you will have a change in potential in getting to the center of the ring. I don't know if you can do this integral, though. I'm really not sure. So this was what we left off with on Friday. This is a quick review of how to get to the answer. This would count as a derivation. So if you're asked to derive an expression for the electric field, this would work. And this is the electric field anywhere along the axis that runs through the center. It is not the electric field for anywhere, meaning this does not tell me electric field right here in space. It only tells me electric field on places on that blue line. Please understand the difference. In your notes, please put that in your notes. That this isn't the electric field everywhere, but it is more than just the electric field at a single point. It's electric field for any point along Z. When we do electric fields, sometimes we do come up with expressions that will give us a lot of answers for the electric field, and sometimes it's just for one location in space. Please understand how to recognize the difference. It would not be crazy to say, what is the, well, I would probably use this. How much energy not a great question in the way it's worded, but a fine question, what I would expect to be able to do in the class. I don't know that you could do the integration, but I do believe with all the skills you you should be able to set it up. It's not hard to set up. So, electric potential. We have an expression for electric potential, one that you are familiar with and should know how to use. We have more than one, of course. Some of them will work, and some of them are more laborious. This one would be more laborious. I'm not sure this is the way you want to go. I do think this is the way you want to go. You have an expression for the electric field. ds represents a change in location. This one would work. Set it up. What would the integral look like? And then express to me why that might be a problem for you. Not a whole lot to do here. All you're doing is dropping in your expression for the electric field. Now, on the actual AP exam, you have to have an expression to be able to do this. Writing this equation out may get you a point to indicate that at least you know what to do. But if you write this equation out and this was the wrong way to do it, then you get nothing. So being able to figure out the different ways to deal with electric potential are probably appropriate here. This actually wants how much energy there would be. So the amount of energy would be multiplying that by Q, because that's the amount of charge you're actually moving. Otherwise, you're just finding the electric potential. So to understand the difference. Now, the electric field, we have an expression. We just did all that. Q over 4 pi epsilon naught. And that's going to be times Z over R squared plus Z squared to the 3/2 power dz. You would change ds to dz to indicate that we're just going to go along that line, that blue line Z, from someplace infinitely far away all the way to 0. Now, could you do this integral with the tool set you have from calculus?
Yes.
I think you probably could. I really do. You're probably going to have to do a U sub. And I think a U sub would probably work best. And I'm thinking, for those of you who know U sub, then maybe R squared plus Z squared probably be the good U sub to you work here. I think that'll actually do the job. This is a math thing, though. I don't know how much of my class time I want to spend on math. Could you be expected to do this on the AP exam? Yes, it's within our capabilities. It's within the purview of the course. If an integral is within Calculus 1, you are expected to be able to do it. Is it going to be something that you can do in a reasonable amount of time or not? Remember, it's probably 1 point for this, 1 point for this with limits, and then 1 point for an actual expression. You'll have to decide whether this point is worth the time exchange. If it's not worth the time exchange, you may not be able to gain that point. And look, you have lots of tests left to go. You have to make decisions. Isn't it going to be du is going to be 2z dz, and we'll just do 1 over 2z du as our subs. I think that works. I think that cancels the z out. So I'm pretty sure this is within your abilities. So I'll have z times 1 over 2z times du over u to the 3/2. Is that our u sub? Did I make a mistake? Yeah.
Would you change your limits according to you?
I actually just usually don't put the limits in while I'm working with you.
Okay.
But I know in calculus you are charged with actually just putting in the new limits.
Yeah.
I was taught different, so I don't do it that way.
Okay.
Make it quick.
Where's the little Q? Because I know that the big Q's
It's right there. I'm not trying to, do something new here. So you're basically having to do this integral. The z's cancel. You can pull the 2 out. And now you just have to take the integral of u to the negative 3/2 power. That's what's in our capabilities. Now, I don't want to spend much more time on this problem. This is math. Do math. What I'm trying to get to a point now is we're at a point in the year where you have to decide whether you can do this mathematics in the amount of time that is reasonable for the exam or you can't. Read the question. Is there a lot more to go? Can you do this in a minute? Because it's probably worth a point to do the math. And if they've given you the answer, you can stop right there. Integrating for that last point, it's not worth writing all the points down, or writing all the sections down. You're not going to get credit for doing U sub, and you're not going to get credit for doing an integral. You're going to get credit for setting up the integral and knowing how the integral will work out in your answer. So you may have to, I would not work out the math if you don't need to for the point. But you need to set up the math. You need to show them that you understand how that part works. Now, I would like you to be able to do the math. That's all nice and all. But I kind of want to leave this question because this question is fine and all the pieces of it are good. And I want to take a few minutes to talk about electric potential. First, be aware going from electric field to electric potential is the integral, and going from electric potential to electric field is the derivative. They share that relationship. So if you're given an expression for the electric potential, you should be able to find an expression for the electric field. And you've been given an expression for the electric field, you should be able to find an expression for the electric potential. Please look at, I think, question number 4 in what I handed you. It's on the back side of the page. You guys see it? You're given an expression for the electric potential that's based on some non-uniform distribution of a non-uniform distribution of charge, with having you go from an expression for the electric field to the electric potential. Again, this is the integral, usually from infinity this is the derivative. Both of these with respect to a path or a position. We know that you have a canned formula for finding the electric potential based on what we just said. This is the formula. And it was derived in 2 parts. First, understanding that it's based on work. Understanding that work is negative of the change in electric potential, the negative of the change in electric potential energy, and our definition of work, which is F dot dx. All 3 of these things combine to give us this expression. Not to mention, I guess there's a 4th. So this expression, which is on your equation sheet, is an amalgamation of all of these functions, all crammed together into one. It's where the negative sign comes from. It's where the definition of electric potential comes from, basing it on work, and then basing it on our relationship between force and electric field. All those things add together to give us this. We used it already a couple times. For example, we have the electric potential of a point charge. Be careful when you use this. Several assumptions went into making this relationship. So whenever you're thinking you're going to be able to go and find the electric potential, this has only a very limited usage. This is by definition point charge, and it's relative to infinity. So it's very, very narrow in its scope. So if you have a point charge problem, then you could probably use this. And we did. One of those ones where I have a charge here, and a charge here. What is the electric potential at this other corner of the square? Does that sound familiar? We did them a bunch. Then there's the other one about how much energy is there in constructing the geometry of this square. And you would have found how much energy there is by placing the first charge. By the way, 0 energy placing the first charge. Then there's energy placing the second charge relative to the first. And then energy placing the third charge relative to the first and the second. And the sum of those things is the energy of the system. We did those. These are all still based on the electric potential of a point charge. The only difference is that the electric potential energy of a point charge, you have to multiply both charges together. These kinds of questions and those, we see them on the multiple choice all the time. That tends to be where they're featured. So